Assalamu alaikum. Dear students, yesterday we studied the basic configuration of buck converter, where we studied that the output voltage of the buck converter V out is equals to Vs time the duty cycle D. Similarly, we derived the equations for minimum inductance required and the capacitance that allows minimum ripple voltage. So today we will perform some numericals that will basically help us to understand the concept of the buck converter. So in this numerical, we are given that the supply voltage Vs is equals to 50 volts. The duty cycle D, that is the time for which the switch is closed, is zero point 0.4. The value of inductance of the buck converter is 400 microhenry and the value of capacitance is 100 microfarad. The frequency given is 20 kilohertz and the load resistance is 20 ohm. So it is our assumption that the components and the switches are ideal. Now we need to calculate the output voltage V out and the maximum and the minimum inductor current, that is I maximum and I minimum. Similarly, we need to calculate the output voltage ripple. So starting from the output voltage, as we know that the output voltage V out is equals to the supply voltage times the duty cycle. So it's very simple. We are given the supply voltage as 50 and the duty cycle is 0 0.4. So we will get the output voltage as 20 volt. Now coming to the calculation of maximum and the minimum inductor current. So in the previous lecture, we studied that I maximum is basically equals to the output voltage time 1 upon load resistor plus 1 minus the duty cycle time 1 upon 2 LF. So since we know the values of every component, resistor, inductor, and the frequency as well, so it's just a plug and play thing. We will put all the values and hence we conclude that the two terms inside the square bracket are basically uh, coming as 1 plus 1.5 upon 2. So from this, we conclude that the maximum current is 1.75, while the delta IL is basically 1.5, because if we compare this thing with the expression that we derived in the previous lecture, so in place of delta IL upon 2, we are getting 1.5 upon 2. So this tells us that the delta IL is basically 1.5. So the maximum current is 1.75 ampere. Delta IL is 1.5. Now we will basically calculate the minimum current using the expression derived in the previous lecture. And again, we get the minimum current as 0.25 ampere. Now, if someone will ask that what is the average current, so it will be 1.75 plus 0.25 whole divided by 2. That is 2 divided by 2, that is 1 ampere. So our average inductor current is 1 ampere. Our delta IL, that is change in inductor current, is 1.5 ampere. Our maximum current is 1.75 ampere and the minimum current is 0.25 ampere. Now coming to the third part of this numerical, we need to calculate the percentage ripple, that is delta V naught upon delta upon V naught. So from the previous lecture, it was 1 minus d upon 8L CF square. So we are given everything, that is the value of inductor, the value of capacitor and the frequency as well. So we can easily see that the percentage ripple is basically 0.00469 or 0.469%. That is less than 0.5%. Now, if we want to basically calculate the effect of ripple voltage, the effect of capacitance resistance on ripple voltage, then we can see that every capacitor has a resistance and an inductance as well. So the effect of the resistance is known as equivalent series resistance, and the effect of inductance is known as equivalent series inductance. Uh, the thing is that uh, most often effect of series inductance is ignored. Why is this so? Because the effect of series resistance is more dominant, or what we can say that most of the ripples are due to this ESR value. So therefore, we often neglect this ESL and we just calculate the ESR value. Now, how can we calculate this uh, ripple voltage to ESR? So it's very simple. If we know the change in the capacitor current, and if we know uh, the resistance, and that is the series resistance value of the capacitor, that is RC, we can easily calculate uh, this ripple using equation 6.21 as shown in this slide. Now coming to the fact that overall ripple voltage is basically the sum of the ripple voltage plus the sum of the ripple plus the ripple voltage due to this ESR. But the effect of ESR is again much dominant. So what happens that we approximately can say we can approximately say that the effect the ripple voltage due to ESR is basically the ripple of the buck converter. So this is the equivalent circuit diagram for the capacitor, that is including the series resistance. Uh, Now for the previous example, if we calculate the ripple voltage due to this ESR, so if the capacitor series resistance is zero point 0.1 ohm, which is very nominal value, what happens that if we multiply this with delta IL, that is 1.5 ampere, we get 0.15 volts, which is much bigger than the voltage voltages that were lost due to simple capacitance. So what happens that if we calculate now the percentage ripple due to only this ESR ripple, so it will become 0.15 upon the output voltage that was 20 volts calculated in the previous example. So it is 0.75%. So if you recall, uh, the previous ripple percentage ripple was less than 0.5%. But when we added this ESR ripple, in fact, when we calculated this ESR ripple, it is alone greater than that entire ripple percentage ripple. So therefore, uh, often we neglect other uh, resources of ripples. We just consider this as the overall percentage ripple. So that was one thing. Now, coming to the fact that buck converters use most of the buck converters use MOSFET in place of the diode. If you recall, in the standard buck converter configuration, we were having a switch and a diode. So what happens that most of the times we replace that diode with a MOSFET. Why we do so? Because a MOSFET has a relatively low voltage drop as compared to the diode. And the reason is basically its RDS, that is the drain to source resistance when the transistor is on. So this is basically dealt here. So inshallah, in the next uh, lecture, we will basically study the boost converter, and basically we will perform some uh, numericals that are related to the uh, design of the buck converter. So let me open the slides of the next lecture. Just wait for a minute. Okay, dear student, this is basically the second lecture of the buck converter, and here we will basically discuss some of the design considerations. As we already know that in performing the analysis of the buck converter, we basically did some assumptions. One of them was that the capacitor is large enough that the output voltage is constant, or in other words, we can say that the ripple voltages are uh, reasonably smaller as compared to the output voltage. So the ripples may be neglected. Similarly, we were assuming that the uh, buck converter is operating in its continuous conduction mode, that is the minimum inductor current is more than zero in any way. So these are the some assumptions that we do. Similarly, we assumed that uh, the switches are ideal, they don't consume any power. If the switch is closed, then the output voltage is zero, then the switch voltage is zero, and hence the power consumed by the switch is zero. Similarly, if the switch is open, then the current passing through the switch is zero, and hence the power consumed by the switch is zero. So these were some assumptions, and due to these assumptions, we basically concluded that what is the expression for the minimum inductance that can be used for the buck converter if it will be operating in the continuous conduction mode. Similarly, what will be the capacitance value that can provide us a percentage ripple voltage that may be ignored, or that is basically sufficient for our application. So coming to those expressions, if you recall, that was the expression of the inductance, that is represented by equation 6.13, that is the minimum inductance that may be used. Similarly, for inductance, we had another expression, that was equation 6.16. So now coming to some numericals. Now coming to some numericals. They are saying that design a buck converter to produce an output voltage of 18 volt across a load resistance of 10 ohm. The output ripple voltage must not exceed 0.5%. The DC supply voltage is 48 volt, designed for continuous conduction inductor current, and specify the duty ratio. The switching frequency, the values of the inductor and the capacitor, the peak voltage rating of each device, and the RMS currents in the inductor and capacitor. So let us start with this example. They are given us that the output voltage is 18 volt and the supply voltage is 48 volt. Since the output voltage is less than the supply voltage, we can easily conclude that it is a buck converter. And we know that for a buck converter, V out equals to Vs time the duty cycle D. So what happens that we get duty cycle as 18 upon 48, that is V out upon Vs. And hence we basically calculate this duty cycle 0.375. Now, what was the second thing to do? Basically, we need the minimum value of inductance that can provide us the continuous conduction mode, for which we know that we already studied this equation L minimum. So we will choose this equation. But for uh, this thing we need a particular frequency. So let us assume that the frequency is 40 kilohertz. Now using this frequency of 40 kilohertz, we basically use this expression of L minimum, and hence we get a value of inductance as 78 microhenry. Now if we add a safety factor of 25% in it, we basically get the new inductance as 1.25 L minimum, and hence we get a value of 97.5 microhenry. In electrical engineering, we basically take a safety factor of between 20 and 25%. So it is not mandatory to take 25% every time. You can even take 20% as well. So uh, hence we concluded that our inductance should be 97.5 microhenry or more. Now for the inductor current or the load current, we know that it is output voltage divided by the load resistance. So since we know that the load resistance is 10 ohm and the output voltage we know it is 18 volts, hence the load current is 1.8 ampere. Now for delta IL, we know that it is Vs minus V out upon L times dt. So we calculated D in the first part of this question. Every other thing is known. So we calculated delta IL as 2.88 ampere. Now we know that I maximum is basically IL plus delta IL upon 2. So using this expression, we calculated I maximum and I minimum is as well. And it is 3.24 ampere and 0.36 ampere respectively. Now for the RMS values of this inductor current IL, we will use the expression that we were using in equation 2.8 of chapter 2. So using those equation, we basically calculated the RMS values of the load current, and finally the capacitance that will allow us the percentage ripple as 0.05, 0.005, sorry, because if percentage is 0.5%, then 0.5 divided by 100 is 0.005. So using that expression that we basically derived in the design of a buck converter, we easily calculated that the capacitor value is 100 microfarad. Finally, as we know that delta IL is basically 2.88, so delta IL upon 2 is 1.44, and hence we basically calculated the capacitor current from that triangular waveform, and it comes as 0.83 ampere. For the switch closed, Vs minus V out is basically 30 volt, and for the switch open, V out equals to 18 volts. Therefore, the inductor must withstand at least 30 volts. So that was all about this example. Now coming to another example, they are saying that power supply for telecommunication applications may require high current at low voltages. And again, the input voltage is 3.3 volt, while the output voltage is less than 3.3 volt, that is, it is 1.2 volt. So we can easily conclude that again, it is a buck converter. Now they are saying that the currents are in between 4 and 6 ampere, and the ripple must not exceed 2%. And one more thing, they are saying that the inductor current does not exceed 40% of the average value. So determine the required RMS rating of the inductor and the capacitor and the maximum equivalent series resistance of the capacitor. Again, using the output voltage V out and the supply voltage Vs, we calculated the duty cycle, and it is 0.364. Now we assumed arbitrarily that the frequency is uh, वालेकुम अस्सलाम, मेरी क्लास चल रही है, बताएं। अच्छा, मैं बताता हूँ किसी को, ठहर जाए। ठीक है। कुछ ना करूंगा। मैं रोटी बना रही हूँ। Sorry, dear students. Actually, I have to take a call. So we were saying that using that output voltage V out and the supply voltage Vs, we calculated this duty cycle as 0.364. Now, assuming that the frequency is 500 kilohertz, we basically uh, use the minimum value of current that was given as 4 ampere. And since they were saying that we are allowing 40% deviations, so we calculated 40% deviation as uh, 4 ampere plus 40% of 4, that is 1.6 uh, ampere as delta IL. Okay, so delta IL is basically 40% of the minimum current 4, and hence for this minimum current uh, and delta IL, we calculated the inductance value, which was 0.955 microhenry. Now, similarly, the maximum current was 6 ampere. And again, we are allowed to take variations till up till 40%. So what we did that for 6 ampere, we calculated 40% of 6 and it comes as 2.4 ampere. So for this 2.4 ampere and the given frequency and the assumed frequency 500 kilohertz, we calculated another inductance that comes as 0.636 microhenry. As you recall, we were having these two inductances as minimum inductances. So if one condition says that the minimum inductance is 0.955 and the other says that the minimum inductance is 0.636, then obviously if we are to satisfy both conditions, then we will take the inductance that is bigger as compared to the other. Hence, we concluded that the allowed inductance is 0.955 microhenry. Again, using the equation of chapter 2, we calculated the RMS values of the current. And finally, we calculated the value of capacitance that allows us a percentage ripple of 2%. So that was basically the calculation or the design of buck converter. You must be knowing this thing that when we say design, we are to calculate the values of capacitor, inductor, and even if the resistor is not given, then we are basically to provide those values of capacitors, inductors, and resistors that meet our design criteria. That is, they basically fulfill the minimum and the maximum current specifications. They fulfill the deviations, that is delta IL conditions that are given in the question. So finally, now if we are given that the series capacitance, series resistance of the capacitance, that is RC, sorry, if we are to calculate this RC, that is the series resistance of the capacitance, we can say that it is the ripple voltage divided by the capacitor current. So the capacitor current for minimum current was basically 1.6 ampere. Using that thing, we calculated that RC is basically the ripple, that is 24 millivolts divided by 1.6 ampere, and it is 15 milli ohm. So that was all about the design of buck converter. Inshallah, in the next lecture, we will study the boost converter. Thank you.